On this video, we're going to talk about section 5.1 in our book on estimating with finite sums. So we start with an example that we hopefully have some familiarity with. We know distance traveled is equal to distance is equal to rate times time. So distance is rate times time. So if we have a constant rate, imagine a train moves at 75 miles per hour for 2 hours. Then we know that the rate is 75 miles per hour, the time is 2 hours, so the distance is 75 times 2 is 150. So visually, you can show that that velocity is constant because it's a horizontal line, and if we mark time along the horizontal axis, then that distance equals rate times time is represented by the area of that rectangle. And you can see that rectangle is 75 by 2, and so its area is going to be 150. Now, that idea of distance being represented by the area under a curve is true when the velocity is variable as well. And so you can see that, for example, if we have this curve that looks variable, then this area between the curve and the x-axis, if that's a velocity curve and this is time on the horizontal, then that area represents the total distance traveled over that time period. Now, separate from that, a particular example is just in general, we can approximate an area under the curve using rectangles. So our book likes to call this the rectangle approximation method, which they abbreviate RAM. So this is how our book does it. That is not universally understood outside of our authors, but you're going to have to see this because you're going to have this kind of symbolism and language used in your homework. So an MRAM is supposed to represent then a midpoint rectangle approximation method. An LRAM means that the rectangles have the left side of the rectangle on the curve, and an RRAM represents right rectangles. So first we'll do one just using pencil and paper, and then we'll do one trying to use our calculator because you're going to need that when the number of rectangles gets too big. So a left Riemann, I don't want to call it Riemann sum yet because that's what we're going to talk about next, but a left rectangle approximation using two rectangles would mean that we are going to take the left side of the rectangle on the curve, use that for the height, and we would get something like that. So we would get those two rectangles. And so that would be an approximation to the area under the curve, where we're going to go the base times height of the first rectangle using the left side as the height, and then the base times height of the second rectangle. So the first rectangle is going to have a base of 1, and its height will be the function 4 minus x squared, where we put in the left side of the rectangle, which is at x equals 0, into the function, so that would be just 1 times 4. The second rectangle has a base also of 1. That's the width of that rectangle, or our delta x, and the height will be the function evaluated at 1, which is 4 minus 1 squared, which is going to be, whoops, that's my left hand touching the screen. And so we would get 7 would be our approximation to the area. Now, the next question is going to be an over or an underestimate, and the idea is you can see visually that we're counting this area here that I'm shading in red as part of the area under the curve, but that's not really under the curve. So clearly it's going to be an overestimate. But the reason, the justification for that, when we're finding the area or approximating the area using rectangles, is going to be because the function is decreasing. So the reason there is going to be because f is decreasing. And that's going to be the only acceptable answer there. So the concavity, it's true that that function is concave down, but that is not what's causing that to be an overestimate. Not with rectangles, it will be with trapezoids. Okay, I'm going to slide the screen up a little bit, hopefully. So now we want to also be able to use our calculator to estimate these areas on the curves when they start to ask us too many rectangles to do pencil and paper. So we're going to do one here. We're going to do a midpoint Riemann sum, and I'm going to walk you through this so you can remember how to use your calculator effectively. So you can go to Stat, hit Stat, and then Edit, and then you should be looking at a screen that has L1, L2, and L3 up at the top. So if you have other junk in there, just up arrow until you're up above here. That's called the formula bar. Then hit clear and enter, and that should wipe the slate clean. Now we're going to do midpoints, and we're going to divide this into four evenly spaced rectangles. So that means we're going to look at, since this is 2 right here, then we're going to subdivide these like so. And so each of these rectangles is going to have a width of 0.5. That's the 2 minus 0 divided by 4. So the b minus a divided by n in general is going to be our delta x when they're evenly spaced. So we want to then put into L1 the values of x that we're going to evaluate in the function to get the rectangles, remembering that this is a midpoint Riemann sum. So the value of x we're going to plug in on that first rectangle, which goes from 0 to 0.5, is going to be 0.25. Our rectangles are a width of 0.5, so the next midpoint of the next rectangle is going to be adding 0.5 to the 0.25 is going to be 0.75, and then 1.25, and then 1.75. So we can enter those into L1. In L2, we're going to get the heights of our rectangle, and so we're going to evaluate these numbers we put into L1 into our function 4 minus x squared. So we can do that by up arrowing up into the formula bar here for L2, and then you can type in 4 minus L1 squared, and L1 I think is second 1 button. And then when you hit enter, then you should have it fill in. It'll fill in all of these heights. And I think the last one's like 0.9375 is what I'm seeing on my screen. Now the L3, what we're going to do is, if we had a variable delta x, we could put the delta x's in there. But in our case, the delta x's are always going to be 0.5. So we can up arrow into the formula bar here and then take our answer that's in L2 and multiply that by 0.5, our delta x. So that's going to give us our height times the width of that rectangle. So I'm going to do that with you here. So I'm going to go L2, which is second 2 button, times 0.5, and then hit enter, and it'll fill all those in. I think the first one's like 1.9688, 1.9688, and then it goes on down to there. So now these represent the areas of each of our 4 rectangles. So what we want to do next is to add those all up. And so we're going to have to go to the sum feature on our calculator. We can find that feature in it's called the list. So if you go second stat, so that's going to be the second, and then the stat button. And then if you arrow to the right to the math part of that menu there, then option number 5 is going to be our sum feature. So if you hit sum and you get a parentheses, then we want to put, in this case, L3. So that will sum everything that's in list 3. So going second 3 button and hitting enter, and I'm getting 5.375. So that is our answer to this midpoint Riemann sum, where we're going to approximate the area under the curve using 4 midpoint rectangles. So let's look at the next screen. So this is kind of a more complicated problem than we could have done at this time last year, but we've kind of been through this once, so we have an idea what's going on. So we're going to find the volume of a sphere. So we're going to take this curve, this semicircle, and we're going to revolve it around the x-axis. And so that volume of revolution is going to result in us getting that sphere. So we're going to, if you remember, try to get this delta volume. And we're talking about taking this rectangle, and as we spin it around the x-axis, it's going to create this, what we have referred to in the past as a disk. And so it's a little mini cylinder there, and we know that the volume of a cylinder is pi r squared h. So in our scenario here, we'll get pi. The radius is, and we're going to use a right Riemann sum here. So we're going to take, I didn't draw this quite right, I'm going to bring it up here. So we're going to put the right side of the rectangle on the curve itself. And so that's going to be our value of the function squared. And the height of that disk is going to be our delta x. So let's see what that looks like. We're going to take then pi. Our function is that square root of 16 minus x squared times the delta x. So this works out kind of nice that we just get to remove that radical. Now, as we do this, if we're going to do a right Riemann sum, and we're going to use 8 rectangles, and our semicircle is going to have a radius of 4. That means as we work our way across here, we're going to have our rectangles are going to be right on these various tick marks there, exactly. So we will start with our first, if you remember, our L1. So our x values that we're going to plug into the function are going to start with a -3, then a -2, a -1, 0, and then 1, 2, 3, and 4. Our L2, the heights that we get, we're going to be plugging into this formula right here. So our formula bar is going to look something like pi times, and we're going to get 16 minus L1 squared, and then our L3 is, well, we can even, on this one, if we want, should we go ahead and just call the delta x here? So we'll go times, and our delta x is just 1. So that will actually give us, in L2, we can do this a little more efficiently perhaps, that will give us all of the volumes of each of those 8 little slices. And so then when we're finished, we can take the sum of the L2s. Okay, I'm going to pause it here for a moment and enter it all in there myself, and then I'll come back and see if we can get the same answer. So when I did it, and my first answer there in L2 was like 21.991, and then when I summed them all up, the answer I got was the 263.894. All right, very good.